How do these two hormones regulate our body metabolism? Okay, first of all, we need to understand that there are many organs and tissues which are involved in controlling the metabolism of our fuel. Okay, so the brain, the liver, the adipose, they are all involved in the fuel metabolism because the brain will not work without sugar, so it needs to get sugar. The liver will make the sugar and supply the brain and the muscle with the sugar. The adipose will store the fat and make this fat available when needed. But these organs, they don't work in isolation. Not, كل واحد قاعد يشتغل لحاله. Okay, so they communicate together. Okay, so how do they communicate together? Do they shout? Do they send text messages? What do they do? Instagram? Okay, no, they communicate via hormones. Okay, so it is the availability mainly of insulin and glucagon that will make them communicate with each other. In addition to the other hormones, such as catecholamines, adrenaline and noradrenaline, also the growth factors, the cortisol, all of these will control the metabolism in our body. Okay? Right. So we need to look at metabolism as a whole. So the full picture, we have integrated metabolism, and this is regulated by the two hormones, insulin and glucagon, in addition to the catecholamines, which play a supporting role. So the catecholamines, can you hear me? The catecholamines will support the role of insulin and glucagon, but the catecholamines will stand on which side? On the side of glucagon. Okay? So the level of this hormone in the body will go up and down, and as they will go up or down, they will tell the body to store energy when we are eating, when we have food abundancy, and it will tell the body to mobilize the energy in the time of hunger or in the time of stress. Why under stress we need to mobilize the stored fat? Because the body is having what we call the fight and flight response. So for instance, if you're walking late at night and you see a dog and the dog starts following you, your adrenaline level will shoot, and the adrenaline will try to make sure you have enough glucose in your body so that your muscles can run. Okay? So this is the picture. So not only when you're hungry, but also under stress, whether it's physiological or psychological, your body will feel that it needs to mobilize the stored energy. How is this regulated? Mainly by the pancreas. So our pancreas has the beta cells, which are in the islet of Langerhans, which make up just 1% of the pancreas. We have the beta and the alpha. The beta cells will secrete insulin, and the alpha will secrete glucagon. Okay? So what is insulin? It's anabolic hormone. So it's going to favor the synthesis of the large macromolecules. So it will favor the synthesis of glycogen in the liver and the muscle. Also, it will favor the synthesis of triglyceride. Where do we store the triglyceride? In the adipose. Okay, mainly. You can store it throughout the body, but it's mainly in the adipose tissue. And also, it will favor the synthesis of protein. Okay, so insulin has anabolic effect on the body because it is secreted in the time of well-fed state. Okay, this is how insulin looks like. It's made from two chains. So it's a small protein, just 59 amino acids, and there is a disulfide bridge connecting the two chains. And there is a sulfide bridge here within the chain. We call it intramolecular or intra-chain disulfide bridge. It is produced as pre-proinsulin, which is like the precursor form. We need to cleave the signal sequence, which helps to direct the molecule inside the cell. Then the proinsulin, if we remove from it the C peptide, the green part is a C peptide or connecting peptide, then you have the mature insulin. What is the importance of the C peptide? As the name indicates, C connecting, so it helps the folding of the insulin molecule. Okay, so the C-peptide assists in the folding of the insulin molecule. So you can. Okay, so this is here we have the DNA inside the nucleus. Then the messenger RNA. So we have transcription, then we have translation. Okay, and this is the pre-pro insulin. The pro, once you clear the signal sequence, you have the pro-insulin, and then once it's excreted, the C-peptide will be released. Actually, the separation starts in the Golgi apparatus, so before even it's secreted, the C-peptide is cleared. Okay, so how is insulin? It's present inside the cell, it is stored inside the cell, inside vesicles or granules inside the cell, and these granules wait for having the order to be secreted, and we will see what will be the order that will the beta cells receive. Why I keep here talking from here? I can't find someone, but I can hear the talking. Okay, so this is how we were going to release the insulin from the beta cells. Let us look at it in this picture here. Okay, so what will trigger the insulin release by the beta cells of the pancreas? So after a carbohydrate-rich meal, the glucose is going to enter your beta cells through the GLUT2, right? And this GLUT2, which is specific not only for the pancreas, remember which other tissue has the GLUT2? The liver. Okay, so the glucose will enter via the GLUT2, and what enzyme is inside the beta cells of the pancreas? The glucokinase. What does glucokinase do?
Phosphorylate.
It will phosphorylate glucose, and therefore it's going to be participating in glycolysis. And then we have Krebs cycle and the oxidative phosphorylation. So this is all what we studied in Mol 1, right? Now all of this will produce what? ATP. So the level of ATP inside the cell will go up. Okay? As a result, this will close the potassium channel because they are controlled by ATP. So the rays of ATP will close the ATP-gated potassium channel, and this will lead to depolarization of the plasma membrane. As a result, this will open the calcium channel because they are regulated by voltage. So this depolarization will open the calcium channel. There will be calcium influx inside the cell. So once calcium is inside the cell, what will happen? It will trigger the release of these insulin granules, okay, which was stored here. Okay, insulin will be secreted. Clear? So in other words, the rise of ATP, which is caused by the phosphorylation of glucose and therefore the participation in glycolysis Krebs cycle, this rise in ATP is the direct cause for insulin secretion from the beta cells. Okay? Clear? Okay. So you can see here as glucose level go up after the meal, what will go up with it? Insulin. And what will go down? Glucagon. Okay, so insulin will follow glucose, but glucagon goes in the other direction. Always think of glucagon as the enemy of insulin. Okay, so they will always have opposing effect and they will work as opposite. This is just a revision from Mol 1. Glucokinase is not feedback inhibitor, so once the glucose level is above fasting, so above 45 milligram per liter or about 5 or 7 millimole per liter, the glucokinase will start working very fast and it will continue working in this sigmoidal shape, and therefore as much glucose as we're getting, as much we are going to phosphorylate. Okay, this is the sigmoidal shape. We studied this in Mol 1. Okay, and therefore this glucose will be used. Okay, once phosphorylated, it will be used to produce ATP, which will open the calcium channel and therefore leading to the insulin secretion by the beta cells. Clear?
Yes. Clear.
Okay, so with this we have explained this one, I think, yes, and this one and this one. Okay, now we move to here. So we have explained that glucose will act activate insulin secretion, right? But not only glucose, also intake of amino acids in the diet and fatty acid will also lead to a similar effect. So your insulin will go up even if you have a protein and fatty acid in your meal. Okay? What about epinephrine and catecholamines? What is their effect on insulin secretion? They will inhibit insulin secretion. So, one thing that you need to know that we have two peptides in the intestine, and these are the GIP, gastric inhibitory polypeptide, and glucagon-like protein, which is actually made from glucagon. These two peptides, they will increase the sensitivity of the beta cells to glucose. So they will make the beta cells make more insulin. Okay? This is why if you give a patient glucose orally, okay, they will have a higher insulin level compared to if you give them IV. If you give them intravenously, you will bypass the digestive system, so you will not have the effect of those two peptides. So those two peptides make the beta cells more sensitive to glucose and therefore make the beta cells produce more insulin. Okay, what about the inhibition of insulin? And when we have scarcity of dietary fuel, so time of hunger, time of fasting, okay, and also during stress, insulin production will be decreased, and this is because of the effect of catecholamines. So in the time of hunger and the time of stress, catecholamines will reduce the level of insulin. Okay? What is the effect of catecholamines? They will mobilize the fuel. Okay, as I said, why you need to mobilize the fuel by catecholamines? Because you need to make sure that you have enough energy for the body to face any danger. Okay, so you will mobilize the glucose from the glycogen stores. You will enhance gluconeogenesis because you want to make sure you have enough glucose, and you mobilize the fatty acids from the adipose tissue. This is the effect of catecholamine. We'll come back to it later. Okay, what is the effect of insulin on carbohydrate metabolism? This is a revision from mole 1, okay? So, what was the effect of insulin on glycogen synthesis and degradation? It will increase glycogen synthesis and it will inhibit glycogen degradation. Okay, so in the liver, it's going to increase glycogen synthesis and inhibit degradation. What about the effect of insulin on gluconeogenesis? It will inhibit gluconeogenesis because, as I said, it is the well-fed state hormone. You know, if you are well-fed, you don't need to ask the liver to make more sugar, so it's going to inhibit the gluconeogenesis. What about the effect of glucose uptake by the muscle and the adipose tissue? The GLUT4 receptors, we said they are insulin dependent. Okay, so insulin will make the adipose and the muscle cells take more insulin through the GLUT4. So it will increase the number of GLUT4 receptors in the membrane. And how does it do that? Here. Okay, once insulin binds to its receptors on the muscle cells or on the fat cells, okay, this is the receptor here in blue and pink. You will have Dr. Moni at the end of the course. He will talk to you about cell signaling, and he will talk to you about this receptor, which is a tyrosine kinase receptor. Once insulin binds to its receptor, it will activate the receptor, and therefore it will lead to a series of events. In this case here, this binding of insulin in orange to its receptor will move those GLUT4. You see the GLUT4, they are the white circles here. Those GLUT4 will be moved. Once they are stored here as vesicle inside the cell, they will move and they will fuse with the plasma membrane, and they will move to the surface of the cell in order to receive more what? Glucose. Okay? So this is how insulin binding to the cells will make GLUT4 available in order to facilitate the entry of glucose to the cells. Okay, and also this GLUT4, the number of GLUT4 can be increased by exercise. So we advise patients to regulate their blood sugar. Why you don't have a chair? Okay, so to regulate their blood sugar, if someone is pre-diabetic and you want to give him an advice, you tell him to exercise more, because by exercising more they will have more GLUT4. This is one way, and therefore they will regulate their blood sugar better. Okay, so this is the effect on carbohydrate. What about the effect on lipid metabolism? In the previous lecture, we talked about the effect of insulin on LPL, right? What's LPL? What was the effect of insulin on LPL? It will increase the activity. So why you need to break triglycerides at the time of well-fed state? Storage. Okay? So this is very important point. Some students, they confuse, because we have two lipase. We have, the two lipase which are able to break the triglyceride in our body. Okay, first of all, where do we have triglyceride in our body? We have it stored in the adipocyte, okay, and we have it in the lipoprotein. Okay, so the lipase will break the triglyceride, but we have two different lipase for the two different type of triglyceride. Okay, the lipoprotein lipase will break the triglyceride inside lipoprotein, which are in the blood. Why? In order to store them. Because you have eaten, if you eat something very heavy, like Pepsi or something, your chylomicron level will go up, okay? You have too much fat circulating in your blood, so the insulin will go up. It will activate the LPL, and the LPL will break that triglyceride from the chylomicron in order to take it into the adipocyte and to store it, and you will become fatter. Okay? The other lipase, which is the hormone-sensitive lipase, the nice lipase, is the one that once active will make you thinner. Why? Because the hormone-sensitive lipase is the one that will break the triglyceride in the adipose tissue. Okay? So it is the lipase that will do you a favor by breaking your triglyceride and in the adipose and making you thinner. Okay? That's why insulin will inhibit the hormone-sensitive lipase, because in the well-fed state, you don't want to, if you are eating, you are not going to use the fat that you store, okay, in your body. Okay, so it will inactivate the hormone-sensitive lipase, but it will activate the LPL, which is taking the fat that came from your capsa. Okay, because you need to store your fat and you will become fatter. Okay, so this is very important to understand in order to be able not to confuse later. Also, insulin has similar effect on protein synthesis, so it's going to facilitate the entry of amino acids into the cell, and it will activate protein synthesis. So this is a summary of all the effects of insulin. You don't need to memorize them one by one. Just remember that insulin is anabolic. It's secreted by the body in the well-fed state, and therefore you can remember all of those. Okay? So insulin will activate glycolysis and glycogen synthesis, protein synthesis. Okay, activate glucose uptake in the muscle and adipose tissue, but it will stop the liver from making glucose, will stop the glycogen degradation, will stop the mobilization of fat. We will talk about this later, but it will also stop proteolysis. Okay? So this is the tyrosine kinase receptor. And this is insulin. As I said, once it binds to its receptor, it will phosphorylate and activate the receptor. And this will trigger a cascade of events. And these events will either phosphorylate or dephosphorylate regulatory enzymes in the different pathways. Okay, leading to their activation or inhibition. It can also lead to alter gene expression. expression, and we will come back to this later. I've mentioned this. This is just a summary. There are additional information here. Don't worry about them, but this is if you want to prepare for the USMLE, you need to know the number of the GLUT receptors and in which tissue they are present. But for mole, you know that we have talked about GLUT2 and GLUT4. Okay, this is a very, very important picture to remember. Okay, so insulin from one side and from the other side are all the counter-regulatory hormones. Okay, so we have glucagon trying to oppose the effect of insulin, but glucagon is helped with the other hormones, not only catecholamines as we will see later, cortisol and growth hormone. Okay, so glucagon, which is secreted by the alpha cells of the pancreas of the islet of Langerhans, is going to its most important role is to try to maintain homeostasis, sugar homeostasis. So it will activate the breakdown of glycogen by the liver, not by the muscle, because the muscle is selfish, as we have learned in Mole 1. And also it will activate gluconeogenesis. This is the most important effect of glucagon, trying to reduce hypoglycemia by making more sugar available, either by making a new sugar, by gluconeogenesis, or by mobilizing the stored glycogen. Okay, glucagon is a smaller molecule. It's only made of 29 amino acids. It is a single chain. Also, it is made as precursor molecules, but once processed, it can give rise to other molecules, including the glucagon-like protein in the peptide, in the GI, sorry. It has a short life. We mentioned insulin. We said insulin has a very short life. It's about 6 hours, and it's degraded by insulin-degrading enzyme. I'm not sure if I mentioned this or no. But the C-peptide, remember the C-peptide? The C-peptide has a longer life compared to the insulin. So sometimes when you do the blood test, you will be able to detect the C-peptide, but not the insulin, because insulin has much shorter life compared to the C-peptide. Okay? Yes.
What happens to the C-peptide? What happens to the C-peptide?
What do you mean after we use insulin? The C-peptide is thrown just to connect. So, you know, it's just a part that's going to be, I'm not sure whether it's degraded or recycled, but you don't have to worry about it. Its job is just to connect or hold the insulin. This life is going to be degraded probably. Okay? So glucagon is catabolic. Therefore, it's going to break and mobilize things in order to maintain blood sugar, and its primary target is the liver. So when the blood sugar goes down, glucagon level will go up. Okay? So in the night when we are sleeping, the blood sugar will go down and the glucagon will go up, and it will prevent hypoglycemia. Okay? But if you wake up and you don't have breakfast and you come to work and you do effort and you don't eat, then you might suffer from symptoms of hypoglycemia. Okay? Amino acids derived from meal containing protein will also stimulate the release of glucagon. So this is important. Glucose, when the level of glucose goes up, it will inhibit glucagon because it's the low sugar that will stimulate glucagon, right? But amino acids will stimulate glucagon. So amino acids will stimulate both insulin and glucagon. Okay, this is important. So if you eat a protein meal, okay, both your insulin level and your glucagon level will go up. Okay, and this is explain why. Where is it? Okay. The glucagon, which is released after a meal containing protein, will prevent hypoglycemia that would have otherwise occurred because of the result of increased insulin secretion. What does this mean? You know, I'm sure you have heard of something called postprandial hypoglycemia. We'll come back to it later. Or transient hypoglycemia. Transient means temporary. Postprandial, post after prandial is for meals. Okay? If you you're fasting you're always advised not to eat or to break your fast with a sugar drink, very sweet drinks which is rich in sugar. Why? Because this sudden increase in blood glucose will lead to exaggerated insulin response. So there will be too much insulin. Your insulin level will shoot. As a result, what will happen? You're still eating, and your body have a very high, sharp rise in insulin. So the patient, will have hypoglycemia. So you might have headache. You might feel unwell when you break your fast with a sugary drink because of this transient hypoglycemia. You get this with the glucose, but you don't get it with the protein, because once you eat with the protein will increase both insulin and glucagon. Okay? So now we will talk about catecholamines. So catecholamines, what is their role? They will support the glucagon. Okay? So elevated levels of epinephrine will stimulate the release of glucagon. We said the catecholamines will inhibit insulin, okay, and they will stimulate the release of glucagon. And actually, their effect is more dominant, or it's stronger than the effect of blood sugar. So if you have a normal blood sugar, let's go back to the scenario of the dog. If you go walking at night, even if you had eaten and your blood sugar is normal, okay, if you see a dog and you are afraid, your catecholamines will go up and they will increase your glucagon level, even though your blood sugar is normal, okay? Because the body is anticipating, despite now the blood sugar is normal, but the body is anticipating that you might be running for a long distance and you might need lots of sugar, okay? So the effect of catecholamines will override the effect of the alpha-cells. It means that the catecholamines will take care of the situation, not the blood sugar, because it is under stress. Okay, so we mentioned that on the carbohydrate metabolism, the glucagon will break down the glycogen and increase gluconeogenesis. What about lipid metabolism? It will favor hepatic oxidation of fatty acids. So we need to mobilize the stored fat, and also the formation of ketone bodies. So glucagon will favor ketogenesis. Why? Because if you mobilize too much fat, we will learn, I think you learned this in the ketone bodies formation, right? If there are too much accumulation of acetyl-CoA, the Krebs cycle cannot cope. This will lead to the formation of ketone bodies. Protein metabolism, like insulin, glucagon will increase the uptake of amino acid, but by which organ? Liver. Why you need amino acid in the liver? Yes, because you will use the carbon skeleton of the amino acid as gluconeogenic precursor. Okay, so this will lower the plasma level of amino acids. This is the effect of glucagon. It's mediated via a different receptor. So this is the glucagon receptor here in rod shape, and this is the protein which will be activated. It's actually active adenylyl cyclase. So once the glucagon binds to its receptor, it will activate adenylyl cyclase. We mentioned this a little bit in MOL 1, but you studied more with Dr. Moni. This will lead to the formation of cyclic AMP, which will activate by phosphorylation or dephosphorylation, and therefore it will control the rate-limiting steps of all these events. So again, you have a cascade of events. And you have all of this triggered by the binding of glucagon to its receptor. So this is hypoglycemia. How do we define hypoglycemia? If the blood sugar is below 70 milligrams per deciliter, you have to pay attention to the units. You're not required to remember them. At least just remember this one, but not all the rest. So below 70 milligrams per deciliter, a patient will be hypoglycemic. He will start having symptoms by 60, so he will feel hungry, he will feel shaky, he will start sweating. These are the adrenergic symptoms because of the adrenal gland, but then he will have the more severe symptoms, which are due to the deficiency of the blood sugar, in the brain. So the brain will become deficient in sugar. So patients can die actually from hypoglycemia. Actually, there was a sad incident in Riyadh where school children died, I think in the Indian or Pakistani school recently. He died because he didn't take his insulin shot. He died from hypoglycemia. No, I think he took an overdose of insulin. Yeah. Or he took his insulin without eating. I don't know, but I know he died from hypoglycemia and he's diabetic. Okay. So that's why, because hypoglycemia is dangerous, we have two overlapping systems to control hypoglycemia. We have the glucagon and we have the catecholamines. Okay? So the catecholamines will have what we call the short-term regulation. So glucagon and helped by the catecholamines will control what we call acute health. It is important in acute and short-term regulation of blood glucose levels. But for long-term, also we need a mechanism, and this is by the effect of cortisol and growth hormone. Okay? So cortisol and growth hormone will help in managing the blood glucose in the long term. And why it is a long term? Because it is affected at the transcriptional level. So expressing more of the enzymes needed for the pathways. Instead of making the enzyme less or more active, you have learned this in the enzyme lecture. There are two ways. You either make the enzyme less or more active, or you control the gene expression. So you make more or less of the enzyme. So it's the cortisol and the growth hormone which take this long-term regulation. And as I said, because hypoglycemia is a dangerous thing, you have to have those two overlapping. One from glucagon and the other by all the other counter-regulatory hormones, catecholamines, growth hormones, and cortisol. Okay, so this is what happened in the blood as the blood sugar goes down. So if it is below, let's say 90, the insulin production will decrease. Then around less than 70, this is when epinephrine and glucagon will start, level will rise. Then the growth hormone, then the cortisol level will rise. If the patient is not addressed, is not treated, he will have symptoms of anxiety, palpitation, shaking, sweating. And if it's even not treated, then he will have the severe symptoms of confusion, seizure, coma, and la death because of the neuroglycopenia, because the brain has no sugar. Okay. So glucagon, as we said, will stimulate the breaking down of glycogen and the making of glucose in the liver. What about epinephrine? Does it do the same thing? Epinephrine will stimulate glycogenolysis only, but also lipolysis, so the mobilization of fat. It will inhibit insulin, as we have seen, and it inhibits the uptake of uptake of glucose by the peripheral tissue. So it interferes with the GLUT4 activity. Okay, so this is epinephrine. So epinephrine is very important in the case of glucagon secretion is deficient, because in the late stage of type 1 diabetes, not only the insulin is not made, we know that there is no insulin in type 1, we'll study this later, but in the late stages, the pancreas becomes so weak, even the body cannot make glucagon. Okay? And this is why these patients can have hypoglycemia also. Therefore, to correct this hypoglycemia, you need to have both glucagon and epinephrine. If both are deficient, then there will be severe hypoglycemia. In other words, if the glucagon is deficient, the epinephrine will help in controlling blood sugar. If both are deficient, this is when severe hypoglycemia will happen. Okay, so these are the different types of hypoglycemia. We have insulin-induced hypoglycemia. We'll come back to it in the diabetic lecture or diabetes lecture. This is observed in patients with insulin. So once they take the insulin, they might suffer from hypoglycemia. So if they take their insulin and they don't eat, or they accidentally take an overdose of insulin, they can suffer from hypoglycemia. So how do you treat that? You give them sugar orally. If it is a very severe situation, then you give them a glucagon IV. So this is what happened in patients with type 1 diabetes. Once insulin is given, you can see here the blood sugar. Once insulin is given, the blood sugar, this is the blood sugar by the way, the blood sugar will go down. If you give them saline, saline is nothing, it's like placebo effect. So the blood sugar will go up by itself. Okay? Why? Because insulin will start be breaking, and also the body will respond by making the glucagon and the catecholamine. But if you give them glucagon, what will happen to the blood sugar? It will rise sharply. Okay? We need to make sure you understand how to interpret these graphs, because you will see lots of them also in the lecture on diabetes. Okay? طيب. We have postprandial. We explain postprandial. What's postprandial? After a meal. It's a type of transient. Okay, transient means it's going to correct itself, and there are mild symptoms. So you might have a headache, you might feel shaky. Okay? So it should cure itself by its own. But how to avoid it? You should avoid it by eating frequent small meals. Fasting hypoglycemia, this is when there is no blood sugar, no intake of glucose for a long time, okay? And the body is using the glucose in the peripheral tissues. If untreated, it can be severe. It can have serious condition, I mean. Okay? This is the last slide. Here we will talk about alcohol intoxication. Okay? So just in case you work outside and they test you on ethanol metabolism, so you should know that those who consume alcohol, in the breakdown of alcohol, they will produce lots of NADH. And to get rid of NADH, the body will occupy the gluconeogenic precursor. So pyruvate and oxaloacetate, instead of being used to make glucose, they will be busy trying to get rid of the excess NADH in the body, which is produced from the alcohol metabolism. So what will happen as a result?
Hypoglycemia.
No.
Yes, if a patient came to you, he drank too much alcohol and he did not eat, then he will have hypoglycemia and he will have symptoms of alcohol intoxication. Okay? So this is to know about alcohol metabolism. I think Dr. Abdul Jabbar will have a lecture about this, but just in case he doesn't, so I mentioned it to you. Okay, with this we conclude. I put the attendance.